So this is an example of an induction proof in graph theory, very similar to 3B on homework 6. But there's some vocabulary and ideas that we'll need to introduce before we do the proof. So here's the claim. Any planar graph, we'll talk about what planar means in a second, can be colored with at most 6 colors. What do we mean by color here? It's what we've usually meant up to this point, right? Colored means that we assign colors to vertices so that adjacent vertices, right, vertices with an edge between them, have different colors. Okay. Right, now what does planar mean? A planar graph is one that can be drawn without its edges crossing. Right, so all paths are planar, all cycles are planar. The complete graph on 4 vertices is planar because we can draw it like this. But it turns out the complete graph on 5 vertices is not planar. There's no way to draw it so that none of the edges cross. And there's one important thing that we'll need to know about planar graphs that we won't prove. So I'll call it a lemma that we'll just assume. It's that every planar graph has a vertex of degree at most 5. Right? There's some vertex in the graph we can choose that has no more than 5 edges connected to it. Okay, so those are the pieces we need. Now, let us prove this by induction. And we're going to induct on the number of vertices, which we'll call n. Right, so as usual, we start with a base case. What's the smallest planar graph? It's a single vertex, right? N equals 1. We can definitely color that with at most 6 colors. I just did. It's green. Done. Okay, so now inductive step. We'll assume it's true for n equal to some k, and then we want to prove it's true for n equal to k plus 1. Okay, so here's another key thing about planar graphs, right? If planar graphs are a graph that can be drawn with no edge crossings, then if we remove a vertex and all its attached edges, we're definitely still left with a planar graph. So what this means is we can look at a graph G with k plus 1 vertices, right? G is this blob. My professor would have said it was a potato. What do we know about this graph? Well, it's planar. And what do we know about planar graphs? Well, the planar graph has a vertex of degree at most 5. So let's choose that one, right? This is V. What do we know about V? The degree of V is less than or equal to 5. So I'm going to draw 5 edges coming out of it. There we go, 5. I'll extend that. There we go. So now what? Well, let's remove V. And we'll look at the rest of the graph, G minus V. So what's left is everything over here, right? This graph has only k vertices, right? So that means that by assumption, we can color it with at most 6 colors, right? G minus V is 6 colorable. Yes, that's a word, at least for mathematicians. Okay, so that's cool. So now what do we want to do? We want to add V back in. And we want to figure out a way to color V that works with how we've colored the rest of the graph. Right? So G minus V is 6 colorable, so let's color it. And then we add V back in. Well, what are the rules about how we color V? It can't have the same color as any of its neighbors. But how many neighbors does V have, right? It has at most 5. That means at most 5 colors, if all the neighbors have different colors, are taken. So there's a color left over. So we can color V, and then all of G is colored with at most 6 colors. And that's what we set out to prove.